Hi there, Dr. P here, and in this lecture video we're going to take a look at orbitals. Orbitals, orbitals! Yay! Now, before we start talking about orbitals, I want to go into quantum numbers. And of course, quantum numbers are going to be associated with or describe different orbitals. And the different quantum numbers have different names, which you don't necessarily need to memorize, but rather understand the rules for them. So we start off with the principal quantum number, which is n. I'll just abbreviate number with the pound sign there. So this has integer values, so n equals 1, 2, 3, etc. And it's related to the size and energy of the orbital. Next we have L, which is the angular momentum quantum number, and it has integer values from 0 to n minus 1 for each value of n. So we will have, well, I'll just write that out here, integer values from 0 to n minus 1 for each n. So if we had n equals 2, we could then have we could then have L equals 0 or 1. And this is related to the shape of the orbital. When L equals 0, that's the s orbital. When L equals 1, that's the p orbital. When L equals 2, that's the d orbital, or d orbitals, I should say. So we've got an s orbital, we've got multiple p orbitals, multiple d orbitals. When L equals 3, those are the f orbitals. When L equals 4, those are g orbitals, etc. Okay, and typically we don't run across g orbitals in the ground, or we won't run across g orbitals in the ground states of atoms. Okay, mostly we'll be dealing with sp and d, and I'll point out where the f orbitals show up in the periodic table. Okay, two more before we take a look at what these shapes look like. Two more quantum numbers. We have m sub L, which is the magnetic quantum number. And this has integer values between L and minus L, including 0. Minus L to L, including 0. And this is related to the orientation of the orbital in space. And then the last quantum number is m sub s, which is the electron spin quantum number. And this is 1/2 or minus 1/2. And this is the orientation of spin of the electron in the orbital. Now, spin does not mean that the electron is actually spinning. It is a quantum mechanical property. We'll talk a little bit more about that later. All right, so let's just take an example here, and let's say what orbital has n equals 2, L equals 1, M sub L equals 0, M sub S equals 1/2. Okay, so n equals 2, so we're going to start off with 2, that's our energy level. L equals 1 tells me that we have a p orbital. So it's a 2p orbital, and M sub L is 0, so it's one of the 3 2p orbitals. Turns out they're all the same energy, that is, they are degenerate. So I'm just going to call this one, this is the 2px orbital. We have x, y, and z. So this is the 2px orbital with plus 1/2 spin electron. Okay? The keys here to identifying the orbitals are the principal quantum number and the angular momentum quantum number. That gives you your, do you have a 2p orbital? Do you have a 4d orbital? Do you have a 6f orbital, for example? Do you have a 5s orbital? I don't know. Now, let's take a look at what these guys actually look like. So our 1s orbital, we'll say here, what do orbitals look like? So 1s is a sphere. There's my sphere and my 3 axes. There we go. There is my 1s orbital standing on the end of a little stick. It is a sphere. All right. Now, we don't have any 1p orbitals because our quantum numbers don't allow for that. But we do have 2p orbitals. So we have lobes along the axes. So we would have a we have a PZ, we have a PX, and these are just sort of arbitrary axes here. And a PY. Now what do these guys look like? Well, here's one. Let me find my others here. There's 2, and there's 3. And these different colored lobes are the different phases. So we have here our PZ, so atom in the center, and then we've got our lobes above and below our XY plane. And then we have, let's say, the Y here, okay, and then our X comes out in front. And so really, in actuality, they're like just kind of all jumbled up here. And what they end up looking like is this. So the 3p orbitals, or the 2p orbitals, there are 3 of them. You have to be very particular with how you say things here, are going to look like this. We have PZ, we have PX, we have PY. Okay. Now we have 3D orbitals. where we have dxz, dyz, dxy, dx squared minus y squared, and dz squared. So we have 5 total orbitals there. Now what do these guys look like? Well, let's see here. First of all, here's the dz squared. It is along the z-axis with this kind of disk of a different phase in the middle. Now we have our different phases here. We've got a d yz, and then like this guy here is a dxz, and then perpendicular with the lobes in the middle of the plane would be our dxy. And then the dx squared minus y squared is in that xy plane, but instead of having lobes in the middle of the axes, they run along the axes. So these guys are in the same plane, they're just oriented a little differently. I'm not going to draw them. They're a little bit of a pain to draw, but just know that there are 5 of them total. And then we have the 4f orbitals, where we have 7 total orbitals, and they're not used for bonding, so not used for bonding, at least not in this text. Now, what about the orbital energies? Well, for a hydrogen atom, the energy of the orbital is determined by n, the quantum number, the principal quantum number. Thus, all orbitals with the same n have the same energy. And an electron in hydrogen can occupy any atomic orbital. And it's in the lowest energy orbital, that is the ground state. And adding extra energy can boost the electron up to a higher energy orbital, let's say from n equals 1 to n equals 2 or n equals 3, and that's an excited state. It's very similar to what we saw with the Bohr model. Now, when do these energies get different? Well, that's when we start looking at polyatomic ions, and things get a little bit different in energy. All right. Well, I think that's it for today, or rather for this lecture, I should say. We've taken a look at pictures of orbitals, and hopefully you get an idea of what orbitals represent. Again, they're the probability of finding an electron in a given space. And we've seen what the 1s, what the 2p, and the 3d orbitals look like, and there are illustrations in the text as well. All right, well, until next time, stay safe out there. Bye now.